don't know, coffee dip.
All right. Hello and welcome, ladies and gentlemen. Kat's going to give us a cold intro. Oh, she's muted. That'd have been so funny to put her on the spot. All right. Whenever
Cold intro.
whenever you're ready, Shane.
All right. Well, here we are over here at the Flat Earth Gang Discord, bringing our communities together on a new platform. And to top it off, we thought we'd do a nice visual heavy presentation on one of the tools that we like to use and specifically are using for the celestial theodolite. There's been some peripheral arguments here. Oh, actually, have you guys tuned into my stream here? Do you see my awesome thumbnail? Let me switch over to that. So yeah, we've been using this tool, Stellarium, to verify true positions of stars, and people have made peripheral claims that actually when we do that, we're invoking the globe, and then only the globe can have observations of the sky. So we're going to go through that claim a little bit and dig out the truth and see if it is model exclusive or model independent. Okay, it didn't change. There we go. So at the heart of Stellarium, it's really just showing you the celestial sphere. So we have to go into exactly what is the celestial sphere and how is it related to coordinates. So it is observed in a hemisphere around the observer. Everywhere you look, you have a hemisphere viewable of stars. Depending on your latitude or where you are, the hemisphere will shift and the circles of arc will incline or decline depending on which direction you go. All of this is based on a flat plane observation with a hemisphere view around the observer. If we look at what we define the celestial sphere as, there we go. Let me see this. There we go. So if we look at how we define the celestial sphere, it's actually an arbitrarily large radius, which is practically infinite. And so it's a practically infinitely radius sphere, which allows things to be mapped as they appear from Earth. So it's geocentric without considering actual distances because we have an arbitrarily infinitely large radius. And an infinitely large radius, geometrically can be equated to a flat plane. Something that curves indefinitely would be flat. There's zero difference, geometrically speaking, between a sphere of infinite radius and a flat surface. So the very first trick we're pulling off is that even though we have an equivalence between flat plane and flat plane and curving elevation angles, then they're going to say, actually, we have a sphere around the sphere with an infinite radius from the first sphere, and that the distance doesn't matter. We can represent it anywhere. And actually, it's equivalent. Is that a question? Nope. If we have questions, you can.
Yeah, I have a question about the geocentric coordinates and like the sphere of infinite radius, right? So in that regard, it doesn't really matter the actual physical altitude of the stars. They can just work the trigonometry off the angle. Is that kind of like the baseline of the stage they're setting for how they're going to derive everything? Okay. So they don't want you to conceptualize physical altitude, but they want you to use all the same trig functions that would be able to derive a physical altitude.
Yep.
Okay.
Yep. And don't forget, they move in an equidistant web. They never change in distance from each other. They effectively act as if they're infinite, right? For practicality purposes. And they treat them as an equidistant web at the same distance for navigation. And that's how you do it if you make them all infinite, right? They're all the same infinite flat plane distance. It's kind of a trick. So the first trick they do is they equate the celestial sphere of infinite radius to the flat plane. And how they conceptualize it is, you have this terrestrial sphere idea, this conceptual sphere that we made up. And then around that, you have the celestial sphere, another conceptual sphere that's infinitely large that we also made up. But from the observer at the fictitious center, we're going to draw a tangent from this sphere to the other sphere, and you can do that to any star on any position because it's always in the center. So you have a series of infinite tangents, and that is the equivalence between flat plane and a sphere of infinite radius. They can literally just use flat plane elevation angles and prescribe them as a tangent on a concentric sphere with a fictitious observer in the middle. that a question or you just hot micing?
Yeah, I hear a mic, but I don't hear any audio.
I heard like a laundry machine.
No, that was me, bro. My bad. I was having trouble looking at it on my laptop, so I switched to my phone, and then when I came in, I was off mic. All right, go ahead. You good?
You watching this on your phone? Oh man, that
Yeah.
hurts my soul.
No, I'm trying to. So when
watching-
I click on your screen on my computer, it's giving me an error code.
All right, hold on. Let me lower the quality and stuff. I put it at like max.
Yeah.
Sorry.
Dude's trying to freaking share a text file at 1080p, 700
Right,
FPS. Like we're in a competitive speed reading comp.
This bitch. I'm like,
see if that's
all right. All right, let's see. Let me get it off of here.
Dude's making my network card overheat.
Your fresh modem might be a little overtaxed and just drop dead or whatever.
Right, I just had to get a new modem because of this. Actually, the guy at Spectrum specifically said, "Do you know someone named Shane St. Pierre, and do you stream with him regularly? Because if so, that dude's got his bandwidth settings way too high, and it's killing your modem."
All right. So, moving on a little bit, we have different ways to represent the same data. If we have an observation that we take from our local horizon, we can then represent that observation in any number of ways. You use Cartesian coordinates, which can be expressed rectangularly, cylindrically, or spherically. So you have spherical, rectangular, and cylindrical coordinates, which kind of all exist in what I call Cartesian simultaneity, just meaning that you can instantly transfer any position and coordinate from one to the other and back again through a lossless method. So there is no loss in data and relationships. There's no ratio. The same data is translated back and forth between these coordinate sets. So the reason we're going into that is because we're saying that you can represent a single observation spherically, hemispherically, cylindrically, with a paraboloid, with a cone, or a hyperboloid. And all the translation back and forth doesn't mean anything. It doesn't change the data in any way. This is all related through the z-axis. They can orthogonal coordinate systems have this specific relationship, is that they have lossless and instant transfer between the two. So just because we choose to represent something spherically, does that mean that it exists as a sphere in reality? Of course not. That's mathematically silly. All right. If we represent it conically, does that mean it exists in a cone? No. What if we took a rectangular observation or put it from a rectangular coordinate system and translated it to the cone coordinate system? It would be the same observation and the same data, and we translate it back and forth losslessly. So it's not telling you anything specific in which coordinate system you choose to represent the data or observations. So the celestial sphere model is a sphere, surprise, right? But it's based on an observable hemisphere. Now, on the globe Earth, one observer only ever sees half the sky. That's how they explain it to you when you're a kid. But when you go to model things like, say, SunCalc or any stellar observation, what they do is they pop an little azimuthal grid around the observer, and that is not half the globe. And then on the globe, they can move this around and they can see observations. Jaron uses it all the time on his model. So it's not actually a half the sky for them, but it is just an observable hemisphere for each observer. So they're literally showing you the celestial sphere observed via one hemisphere at a time for one observer. So that is moving on to angles based, coordinate systems based on angles to the stars. So we have latitude and longitude and the celestial coordinate system of right ascension and declination. So celestial coordinates, right ascension and declination, and they represent them like this. Again, we have our flat plane observer, we have our hemisphere of stars around it, we have elevation angles dipping and changing as you change latitudes. And then back at the beginning there, we had it also represented with the celestial sphere and the concentric sphere around it. So again, this is all just right ascension and declination and how it's portrayed on any educational site, right? A hemisphere of observability, and then over here, a sphere around another sphere of infinite radius. So you have concentric spherical coordinates and your hemisphere of observability. It's always represented this way. Everywhere you look, right? They choose a hemispherical coordinate system because they just mathematically create the bottom here. The only thing being observed is the top, only ever being observed. We'll get into how you represent coordinates below the fundamental plane here, but for everything for right now, we're sticking to just regular observations above this hemisphere of observability. And they mark it with the arc and the antarc of these celestial transits. So either goes this way or it either goes this way, depending on how far north or south you move. So again, this is the representation of the celestial sphere, a sphere of arbitrary radius, and it's based on this, a hemisphere of observability. This is called, this is from an ancient book called the local, from astronomy, and it's talking about the local celestial sphere, which is just an observer-centric hemisphere, which you can make measurements in, right? The zenith is directly above. You can take an azimuth, which would be from true north around the circle, 0 to 360 degrees, and you can take elevation angles above this horizon, usually 0 to 90, right over here. And using these sort of metrics, you can describe coordinates. This is another representation of the same thing, how you would see the sky. That is from a manual on installing solar panels, but when they're talking about the sky and how to position the sun, they talk about the sky dome and the visible hemisphere of the sky above the horizon in all directions, and they're describing it very similarly to how we just described it. And again, you'll see this conical shape, this hemisphere of observability. This is what's at the backbone of all stellar observations. And in fact, all stellar observations are modeled this way. This is a local alt-az grid, right? You can tell where the North Celestial Pole is. We're looking at the arcs of the celestial bodies as they rise and set in front of us. What this coordinate system is called is the altitude, azimuth, or the horizon, also known as alt-az commonly. The altitude azimuth coordinate system just has a zenith, like we said, directly above. The horizon is the fundamental plane the observer stands on. Altitude is the angle above the horizon to the star. That's this over here, 0 to 90. And then the azimuth, angle from true around this circle. So if true north is over here, then 0 to 360 marks around the circle. And that's how you would make measurements. And again, this is at the heart of stellarium. This is what you would see with the alt-az grid. It's called the azimuthal grid. That's where we got the term from. So again, coordinate system alt-az is also depicted like this. This is an actual model you can get where they shove this globe Earth in the bottom, but they're modeling it correctly with the hemisphere up here. And again, all the same visuals, all the same demonstration, and this is what we're talking about. Now, if you wanted to relay to somebody else some observation that you made in this alt-az coordinate system, you wouldn't be able to, because you'd have to have a unifying point, a place where you both could count from 0, or an equator, a common unifier, an equatorial based system, something like right ascension and declination, which is still representing your alt-az observations, but it's referencing a common line called the celestial equator. And from that equator, they start to make measurements that are synonymous with each other. So you could tell someone across the flat Earth an observation that you made, and instead of giving them your local alt-az coordinates where you saw it, you would give it to them where they would be able to see it by using your local time, converting the local hour angle calculation, which is comparing your local time to Greenwich Mean Time, and then using that to get the proper right ascension, to get the proper declination, for them to make the observation that you made. If we were just using local alt-az, we would have a different elevation. Azimuth would be different. There would be no commonality. You wouldn't be able to make observations that way. So even though everyone observes a hemisphere, there would be no commonality. No, even, or to relate it to other observations from across the Earth, you'd have to have a common unifier, and they do that with the celestial equator. So the main difference we're trying to put forth here is that if we have a hemisphere of observability with a fundamental plane, then what's the difference between representing something hemispherically like this or spherically like this? And again, this is the same point. This just has a negative z value. So literally the only difference between these two, hemisphere and sphere, or flat and globe, is the fundamental plane, where we talk about positive and negative coordinates. It's just this plane, meaning that any observation for below this axis, below this 0 point, would be negative. So the z can go negative. And there, ladies and gentlemen, is the only difference between a spherical coordinate system and a hemispherical one. So when you say, where does the star go on flat Earth? Well, it goes around you, but we represent it with a negative coordinate. The best way to envision this is with this model here. If you're looking at the model here, the circumference of the circle that we're looking at is not beneath our feet. The actual circumference is the track of the celestial body around the Earth. this is the circumference of the circle that would determine predictability and sunrise times and when it comes back around, as you see here. They imagine it that it goes beneath your feet over here, and they complete a circle of the same size beneath your feet. And they say, look, when I don't see it anymore, when the sun sets, if I focus my equatorial mount below the ground and I just, progress 15 degrees per hour until it comes back around, as soon as it rises from me, I'll be pointing right back at it again. And that gives them the illusion that the stars and celestial bodies go beneath their feet when they don't see them. But if you look over here, you can tell that this circle is the actual circumference that would determine the predictability. This is the track of the celestial bodies, the sun included, and this is the size of the circumference that matters. And this is the mathematical representation of that value. It looks a little bit different over here, but again, the representation is the same. We're representing the celestial bodies in an equidistant web around the observer, all at a fixed distance, in this case, 6210, which is the maximum distance we can display a celestial body when we're trying to compare flat to globe. Any questions so far?
So the maximum distance and latitude lines multiplied out that represent the 69 mile per degree relationship to Polaris ends up to be 6210.
Yep.
Is that what
yep.
Yep. So that infinite radius thing, just conceptualize it as an elevation angle. Never think of it as an elevation. That's what the reverse would be, right? Because it's just trig.
Yep. Yeah, I don't disagree with that. Right. That would be the actual implication where we could represent it this way. Exactly. If you do, coincidentally, if you set, your vision radius to 3959 and you do basic trig, sine and cosine to get elevations and distances based on, basically this triangle over here, then yeah, when it's right at the horizon and when it's right above your head, you'll see it maxes out at 6210. So both the distance from the North Pole to the equator and a quarter terrestrial meridian is the same value as, or the maximum distance the star we would observe in a fictitious point around us when we have a vision radius of 3959. It's weird that those two values are exactly the same, isn't it?
Identical.
When we get to stellarium and how it represents positions, we have to know that it's representing the two-sphere model, the conceptual terrestrial sphere and the celestial sphere, which is how they represent them together. So again, we went over a little bit a while ago with Ptolemy's two-sphere model of the world. It's very much in effect in modernity. They have two conceptual spheres, the terrestrial sphere over here, latitude, longitude, the celestial sphere over here, right ascension, declination, and they map these two things together. And this is the heart of celestial navigation. It's also how they birth the ground position, the GP of a star. When a star is at its zenith or transits over a person, then it has a specific position on the terrestrial sphere at that time. Said another way, if it's 1-for-1, for every point on the Earth, specified by whatever you want to make it, there is a unique point in the sky, right? So every point in the sky uniquely corresponds to a point on the Earth at a specific moment because of sidereal time. And that is at the heart of celestial navigation. So what they do now in modernity is that they convert your local alt as observation of the stars into your right ascension and declination so that they can convert that right to latitude, longitude. So they use this convert longitude to right ascension, and they use the hour angle transformation, as I said before, and that you can make your local alt as observation, which it could be a flat Earth observation, convert that to right ascension declination by using that terrestrial equator and celestial equator, so you have a common unifying point, and then you can represent them in this other coordinate system. From there, it's easy peasy to just translate it 1-for-1 because you have the direct relationship between longitude and right ascension and declination and latitude. Those two things are synonymous. So once you make your observation, translate it to right ascension declination, you can then translate it directly to latitude, longitude, which is how you do modern celestial navigation. Now, in stellarium, when we're talking about how stellarium represents it, we would look at it like this, as we said before. If we're looking at it at half of the view of the sky at any given point, then this is what we see with all the angles mapped out. Of course, this is what it's based on. Here's the actual circumference that we're using. And what stellarium shows you is this, first of all, right? A local observer, and it makes the sky rotate at the correct sidereal time. What you'd want to do though is zoom out, put it in orthographic mode so you can see the actual representation of the coordinates that it's showing you. And here we have a rotating hemisphere, which is now, but we can make it a sphere by going into Alt As. So we've turned the Alt As grid on in Stellarium. This just puts, as we said before, the zenith above the observer, and we can make azimuth measurements around the clockwise from the 0 point in north, and we can make elevation angle measurements above the horizon. So Alt As, very useful. The problem is this zenith just travels with you, and it's always centered above the observer. So to make the equatorial distance, we put on the equatorial grid, which is an option over here. And now you can see the celestial poles, the north and south celestial poles. So we removed the Alt-Ad grid, and now we have a concentric equator where we can make unified observations to another observer. So that's what Stellarium is at its heart. It's doing the exact same thing. If we looked at it all together, it would be represented like this. So here's Stellarium doing its orthographic view, how it's going to represent the celestial coordinates with an Alt-As grid. Here's the math representing how we would math out the Alt-As grid using the same representation. Here's the actual circle that we see the path of the celestial bodies taking in actuality, and we know that we're modeling it below us. A question?
No, my bad.
You have like a super loud white noise. Whenever you're being really quiet, it's really loud. So real quick, what Stellarium is really giving us then is the true position. When we're referencing Stellarium for the celestial theodolite, although we are using the azimuthal grid and equatorial grid to mark elevation angles to get the star to know our true position, when we say the true position, we're actually referring to something like a nautical almanac, or when people would make observations of where things were in the sky, they would make a central reference point. They would write down the angle that the star appeared at and the time at which it appeared. Those two observations together give you useful data for which to navigate when you can't see land. If you know where the star will be and what angle it will appear at, you can use that to make measurements and make navigation, right? Now, when we talk about Stellarium specifically, we always say it's just a reference point to the first cusp of Aries, and we add 15 degrees per hour. This is a visual representation of what that looks like. You're referencing a position of a star, but as this is spinning, you got to know where the 0 point is. Where do you start? So it's called the first cusp of Aries is just it's a known epoch. An epoch in astronomy is just a specific moment that you use as a reference point for coordinates like orbital elements. It's just a fixed snapshot allowing us to calculate positions based on that. And what we refer to the first cusp of Aries, that is an epoch in astronomy, right? And it's the location of the March equinox and just serves as a 0 point for right ascension and celestial coordinates. So what it looks like, if you get a regular star map with all of the constellations and the ecliptic for the sun, and we have the zodiac over here with all of our major constellations, and you can see that we have marked clearly the first cusp of Aries somewhere over here. There we go. And when you change that same equatorial map projection into an AE projection, then you see the, say the circle of the stars. So we still have our first cusp of Aries over here. Where is it over here? So here's Aries. And when we translate it to an AE map, we have it over here. And here's Aries again, the first point of Aries. Now, when we have a reference point, we need to reference this 0 because the stars move. They shift. If we were to look at it over the AE map, if we just take the stars and rotate them a little bit, they would rotate like this above flat Earth. So just because we know where this point is, doesn't help us too much unless we know what time it's going to be there. So we know that this is a latitude circle around the Earth, and that this reference point, this epoch, this 0 point, is also moving. So when we're trying to count from this point, we need to know where it is and what time it's going to be there. And from this sort of demonstration, you get an actual map of the stars rotating at 15 degrees above the flat Earth, with latitude circles that never change, and an equidistant web where the stars are always the same distance from each other. And it looks a lot like this. The actual stars with the ecliptic, this is over here, and the zodiac, which is over here, and they rotate at 15 degrees per hour. If we look real close, we can find the first cusp of Aries. It should be over here, I think, if I can read that. And it's the same position. So again, we're just referencing a 0 point as an epoch to make measurements of where that true position is. So for the celestial theodolite, when we say, what is the true position? We're just referring to where that star was at the first cusp of Aries, meaning the 0 point of the epoch that we chose at this point. So its true position is just, where does the nautical almanac say it should be? If I want to get the nautical almanac out and convert my local time to sidereal time to get my Greenwich Mean Time and do my own calculation from right attention declination from alt as to right attention declination to latitude longitude, I can do that, and I will get the same true position for that star that Stellarium gives us. Now, if we go into the source code for Stellarium and see what it's actually doing in real time, it says right away it's using a geocentric coordinate system for internal calculation to simulate the night sky. Celestial coordinates are transformed into horizontal coordinates, altitude and azimuth, relative to the observed position. So this is why we spent a little bit of time going over coordinate systems, right attention declination, and alt-az, because, as I said, at its heart, it's just doing this coordinate system transform. It's taking your normal observations of alt-az in your hemispherical grid and converting them to right ascension and declination via the equatorial comparison point, where they have a unifier. To further look at some of the specific functions that it's calling when it's doing the neat things that we see it, we look at converting from geodetic latitude, longitude to geocentric. That's over here. Updating position is just geodesic to observer geodetic. This is literally the function stel core, right? So this is what it's doing. It's just doing coordinate system transforms, and it has commented out a light description, convert equatorial coordinates to horizontal, which again is the basis for what it's doing. And what that is this. This is the same thing, converting horizontal to alt-az. If we were to look at what it's doing in real time, this is exactly a representation of what Stellarium is actually referencing. And again, if we put them side by side, you can clearly see that this model is modeling the same as this model, is modeling the same as this model. So they're all just different visual representations of the hemisphere of observability that anyone has over the Earth. So what we, again, just to sum it up here before we end out, is we have a hemisphere that is equivalent to spherical as the coordinate systems go when we're representing it. The only difference being this fundamental plane value where it goes below the horizon, and it can be represented as a negative coordinate. And when we reference it for our celestial theodolite, we're only referring to the true position of a star, from the nautical almanac, as reference to a 0 point, which is our epoch, which is reference to where the star was as it spins around the Earth on the first point of Aries as any position around the Earth. That's what we're referring to. That's what we're using it for, and that's how it's doing it. And that's pretty much what I got on Stellarium. You guys got any questions?
No, not really, man. It's pretty clear cut. Kind of going kind of fast, but we got no questions though.
No, we can go back through it all. It's a short presentation. That's
I don't have a question per se, but the relating the ground positions of the stars at a particular point in time is what is said to be like the mutually exclusive way to do navigation, and this is what truly revolutionized and united everything. But you can actually derive longitude another way by relating the positions of the star to when it transited over a specific time or a specific location, rather than going to where it was at the zenith and taking that snapshot. So you can do like an equivalent method doing the exact same thing, which is what the Chinese did before the Royal Society came through and presented all this celestial sphere stuff with the first point of Aries, and just kind of like redoing what the Chinese already did. But instead of relating it to transits over Beijing at a specific time, they related it to ground positions at a specific time for like 37 stars. Because I think what was the base almanac? It was like 37 navigational stars or something like that, right? There's not that many. So yeah, they just took zenith measurements of those stars and then adding 15 degrees per hour to that, that's when it would complete its circle to return to its location. They just come up with corrections, to place it where they need it to be. But that's what the whole thing is based on, because we don't see that true position, but like the best possible chance of ever seeing it was when it was directly above somebody at a specific time, forever ago, and then relating that in perpetuity to 15 degrees per hour. Yeah, great Prezi, and the negative coordinates
Oh shit!
again
What
super
was it talking?
sorry, super significant. Because we're told, like, that's the mutually exclusive or the mutually exclusive dynamic cause of why the star isn't visible. And it's like, if the star goes in a circle and you just can't see it anymore, it doesn't matter if you plot it as a negative function or whatever. Mathematically, it's representing the same thing, because that was what you see as it gets further, in the sky. As it gets further off into the horizon, it gets lower in the ground. So at that intersection point, at that fundamental plane, right, you just because it's going to return to you regardless, following a 15 degree per hour relationship. After it crosses that 0 point, you just throw a negative on there, keep plotting it out till it comes back positive. You're good to go.
Yep.
It makes no difference.
The predictive ability is based on the circumference of that circle, and you're mimicking what's not the real circle. The real circle is it's arcing out across the land, and as it comes and goes, it appears to rise and set, and you're just making you have the same predictive power because it's just based on the circumference of that circle. And also, I was saying that longitude is really just always converted to time. So the old school Chinese lads, as Alan was finding out in our presentation this week, had a genius way to calculate longitude, meaning time, and they would use a gnomon, which is like an 8-foot stick, and they would stick it in the ground. And they had such a in-depth way to measure the shadows. They had a shadow table to compare shadow length measurements to. So using a shadow measurement of sunrise and sunset on any day, by comparing it to their rotational tables, they could tell exactly what time it was. And with that information in hand, they could use their own longitude system, because they could make their own mean time, their own 0 point. Doesn't have to be Greenwich or any, like we have today, but any sort of epoch, right? They have their own reference at 0, and then they can make shadow measurements to determine the longitude, convert it to their local mean time, and boom, they have their own navigation system using the stars as a flat plane and shadows. I think it was brilliant.
Stiction shadows got him again.
Right. So here's a nice visual of something, a map, a ship sailing through the ocean, and it's represented simultaneously as a equatorial cylindrical projection back here and as an orthographic sphere. So according to a glober, I guess this is spherical coordinates. This trip only exists as a square. It doesn't actually exist also as an orthographic globe, and it definitely isn't flat. This is square coordinates over here. I'm like, no, you can represent them in any specific coordinate system that you like. Cartesian simultaneity is a thing. Spherical, cylindrical, hemispherical, hyperboloid, conical. Doesn't matter. The math, it just makes it lossless transform. So it makes no difference what coordinate system you choose to represent your observations in. And of course, the one that we use is spherical. And the Glober argument is that because we represent it in spherical coordinates, that equals Earth sphere. You lose. And that's very, very wrong on both sides of the argument. That's very wrong. You'd have to relate that spherical coordinate system to the Earth, to the surface of the Earth. You'd have to say that the surface of the Earth is curving at the same rate, and then you'd have to do measurements of that surface curvature rate. Now, what I just outlined is what is called a geodetic datum, actually, which would be how you would connect an abstract coordinate system to the surface of the Earth. And there's a presentation I did on it before, but most commonly known WGS84 is an ellipsoid model. It's also the geodetic datum behind most maps. The latitude longitude system that we are mapping is really just at its heart WGS84, which is an ellipsoid model, which is an assumed conceptual sphere, which would have to be confirmed with surface measurements, which they never did. If you look at how they confirm ellipsoid models, they do surface measurements with meridian arc measurements, but they actually measure less than 1% of that meridian arc to deduce the actual shape of the Earth. So it's very much assumed. They measure about 2 kilometers on the surface of the Earth with rods and chains. They then calculate the rest of that difference using astronomic latitude, meaning latitude determined from the sky. So they're taking a tiny measurement on Earth, usually about one tiny dot, and then they calculate the rest based on the latitude, and they go boom, sphere. And that's how the ellipsoid model is confirmed. And that's the only way in which this abstract spherical coordinate system supposedly gets tied to the surface of the Earth. Very flimsy. So, can people who observe a hemisphere represent their observations spherically? Absolutely. Absolutely, we can. Does that mean the Earth is a sphere? Clearly not. What do you guys think?
Seems very
everyone?
hemispherical, at the very least.
What do you
If
think of
your
this one,
cell
Alan?
phones, sorry,
Go ahead, Lily.
if your cell phones and your computers work, that means it's a globe. I'm sorry.
Solid argument, Lily. I think this one really sums it up. What do you think, Alan? You got the math behind the conceptual sphere, the circumference of the which value we're referencing, and the actual orthographic representation in both grids.
Yeah, that's one of my favesies.
Can you break down one more time as far as the how we see as far as our vision? You said this the 3959 mile radius, like as far as how it matches.
Yeah. So this right here is the math for a vision radius of 3959. So if you were to just assume and extend that, the radius of your vision extending in all directions is 3959, you don't see forever. It has a limit, and that limit is as if you were extending it, an arm away from you at 3959 in every direction. What that would create, though, is a
My bad, Shane. What would be the 3959? What would be the unit of measurement as far as your vision?
3959 miles, right?
Oh.
So talking about your celestial vision, right? Not like on the surface looking at a ship, but anything in the sky that's a star, the sun.
It's 39 feet. It's 39 miles regardless. So
Yep.
Okay. Yes.
For all the stars specifically, they treat them in this equidistant web. And this little sphere right here is just some basic trig. So if you assume that the hypotenuse here, the limit is 3959, and you use basic sine and cosine to get the elevation and distance of the star over here, it's portrayed up here. So you can see as it follows it, this distance is actually the distance where this star would be on this geodesic arc, because we're looking at a hemisphere. So this would be a curved distance over here, and this is 6210. It's the same way. So they represent 6210 because they say that's a quarter terrestrial meridian. Or if it's 69 miles per degree, statute miles, and there's 90 degrees of separation between the North Pole and the equator, then you have 90 increments of 69 miles, then 90 times 69 gets you 6210. That's where we get that figure. And that if this was this was a globe, 6210 is a quarter terrestrial meridian. So it's this distance from here to here. It's 1/4 of the circumference, 1/4 of the way around the sphere. That's where they get it from. And again, we're emulating the same distance in our vision radius with the same hemisphere of observability. And again, that's just based on this. Right, same concept. If the Earth is flat and we only see half the sky at any given point, and if our vision doesn't exceed forever, as probability and contrast limiting and angular resolution and everything would tell us that we can't see forever. If we take it all into consideration, then we get this. Then we model everyone sees half the sky. This follows you wherever you go, and then you can represent the celestials just like this using this based on math. Lo and behold, if you look at Stellarium, they think exactly the same thing. What do you know? And here's the code that actually does the exact transform. Yeah. The reason it looks similar is because they're all using the same functions. They're all doing coordinate system transforms from alt as to celestial. So. And that's why when we prove that the surface of Earth isn't curving with the celestial theodolite, we are certainly allowed to reference a reference position based on where it appears at the first cusp of Aries at a certain time when it rotates around the flat Earth. We're definitely allowed to reference the sky. To say otherwise is silly.
You fail to prove that the Earth is curving, sir.
Right, and it should be mentioned that in our main position, our null hypothesis position for a flat Earth is that curvature cannot be independently verified outside of the stars. Right, everything we find has them referencing the stars for to prove curvature. Geodetic surveying has astronomical latitude corrections. The geoid has gravitation, the gravitational perpendicular relationship to gravity, like the requirement of the geoid, all of that. So yeah, guys, visuals are awesome, right? You can't have a conversation without visuals. Imagine having a debate with someone and then being like, "What? What's this?" You can just shove. Were you arguing about this? Was this your position? Oh, you mean this star that we can't see that everyone can look at?
So
I
it
think
turns out the North,
What?
Peace, fellas. What up, man? This is Jamal. Can you just break down real quick the how they got the geoid, like finding out what down was and how they like what methodology they use?
Certainly. Hold on, let me change
Oh,
presents though.
to find down, you just gotta consult a plumb bob and a star.
Yep. Yep. Switching up prezzies real quick. Pop over here. So the geodetic datum is what we got a reference for that. And how they confirm it is, as I mentioned briefly, and I kind of sailed through, is they use the ellipsoid and the geoid. Here's the geoid model, which is an equipotential surface, which literally is defined by its directional relationship to gravity. So it's perpendicular to the gravity vector. That's literally the definition of the geoid. It's one of the goofiest things. And what they use it for is to reference the orthometric height above the ellipsoid, which they use the geoid above the actual surface. So they use this convoluted method of 3 models to convert their heights to ellipsoidal heights. But how they confirm it is what's called the deflection of the vertical, or an astrogeodetic deflection, which is what we commonly call it, right? It's an astrogeodetic deflection, where they align this plumb bob down on the surface of Earth, although they drew it here. They never actually reference the surface of the Earth. The deflection of the vertical is between these 3 models. They got a plumb line for vertical, and they have the deflection based on the perpendicular to the ellipsoid and the direction of the plumb bob. So they have, here's an actual 3D cutout of what's going on over here. You drop this plumb bob, this tiny section is blowing up over here, and here's the side profile. So you have the 3 latitudes they're comparing, they're deflecting the geocentric latitude, geodetic latitude, and astronomical latitude. So the local coordinates, and then longitude, latitude, and then actual compared latitude to the stars. So what they're comparing is, hey, we have an X, Y, and a north-south vector here, and we're not quite straight. And the degree to which we're not quite straight, we're going to call the deflection of the vertical. And we know that because of the gravity potential of this plumb bob not being quite straight, that the difference here can be measured and observed. And they put the differences here in astronomical tables, and then they use those tables when they do references to get celestial navigations back. So that they're referencing the stars on the geoid to align to the model to do an astrogeodetic deflection. And this is one of the ways they, quote, confirm their assumed and assumptive ellipsoid model, right? Their abstract coordinate system.
So when you say the plumb bob is not straight, you don't mean it actually isn't straight. You mean in reference back to like the geoid. I mean the sphere, or whatever.
Yeah, like, so if I dropped a plumb bob, it'd be straight as hell, right? Because I'm a flat earther and I'm not retarded. But if they drop a plumb bob, right, they have 3 models to go through: a geoid gravity potential vector to wade through, an ellipsoidal normal to sort of elevate through, different heights to get through with trying to do ellipsoid, geoid, orthometric. So yeah, they can't be quite sure that thing is vertical. They don't really know where down is. The whole point on if you're living on a sphere and everyone's down is the infinite tangent towards the center of that sphere, then how are you sure that your level is level? That's sort of a problem they created. But the convolution is the point, right? They created the three models so that they can. This is actually one of the ways they make sea level curved. You know how Glober said level is curved, and we kind of laugh at him. Well, joke's kind of on us because they kind of did exactly that by using these three models. They took what's known as mean sea level and they just wrapped it around their ellipsoid model by using the geoid and orthometric height, and that the specific formula h equals h plus n, where they're converting orthometric heights to ellipsoid heights so that they actually made sea level curved, them bastards.
So the more surveying they do, the more data points they get, the more robust this end user experience globe gets, the more convincing it gets.
Yep. The astrogeodetic deflection is definitely one of the big ones. They do it all the time. They reference it in lots of papers. It's always based on the gravity vector, and it's one of the biggest ways how they know they live on a sphere because they have to constantly correct for it and adjust all their
Dude,
tables. Crazy.
So think about how crazy that is, right? You drop your plug bob, it's definitely down, right? But then you look up at a star and you're like, this star is supposed to be in the center of my transit instrument here, and it's not. So you know what
Not
must be
quite
the
there.
you know what must be the case? The gravity
Dynamics
coming from
filling
the
the
center, yeah, the dynamics of the gravitational potential of Earth isn't quite what it should be in this area, and I need to adjust my plug bob by like 30 arc seconds. Like I forget the amount there, but like wasn't one of those deflections like 2 or 3 arc seconds or something ridiculous? Stone pointed out. Like these aren't
Yeah.
even real amounts. Like when they talk about spherical excess, I bet you're like, oh dude, what is it, like 190 degrees? Like 100, like how much higher is it over 100? Guys, it's like 180.0000000000034.
Yep.
And that comes from zenith measurements of stars. Not even from like, oh, we actually measured the ground with a tape measure and found ball curve or anything like that.
No, well, the other way they confirm their geoid model is the Eratosthenes method, where they use sun angles and the assumption of a radius and a known distance, and they go, boom, ellipsoid model confirmed, because we know sun's rays are parallel and we know how far apart these two things are, right? So it's not a good way to confirm that the surface of the Earth is actually conforming to the model that you chose, but hey, the point is they don't even have to do it that hard. They don't have to try. They don't have to prove it. Nobody's trying to doubt it. What the actual geodetic datum is, like what the ellipsoid model is, what WGS84 is a internally consistent self-referential model, meaning that measurements taken, will always comport back to its coordinate system in which it was taken, and calculations will always remain internally consistent because the measurement unit is derived from the coordinate system. Is everything in there is designed and contrived to reference itself and come up spherical. So an ellipsoidal model doesn't actually prove the surface of the Earth is curving. Just because WGS84 is based on a surface ellipsoid, or based on a reference ellipsoid rather, which is utilizing the geoid and the coordinate system to do orthometric heights via the ellipsoidal model to pretend to measure the Earth, right? Just because WGS84 works doesn't mean that the surface of Earth is curving. Is used in maps, cartography, GPS, surveying, satellites. This ellipsoid model is everywhere. It's literally like the whole world that everyone thinks they live on. It's the reason why people think we live on a sphere. But if you look it up, if they define it, it's literally an abstract coordinate system with a reference surface that they're trying to provide known locations to create maps. So it's a horizontal datum. That's what they're saying. And it has an abstract coordinate system. And when you go into proving it, you get all this crap. You get deflection of the vertical with geoid models, orthographic height differentials, geocentric latitude adjustments. To actually measure a meridian arc, which is where the other place they pretend to confirm the model, they literally measure 1 to 2 kilometers and then go, boom, confirmed it. And in the Geological Society from Africa literally says, well, if you're going to confirm anything, you need to measure at least 70 kilometers continuously, and that should be enough to distinguish a good meridian arc. But they don't even do that. When they get to it, they measure less than 1%. And so 2 kilometers, 70 kilometers is not. If you're gonna do it, you have to measure at least 70 kilometers, and that's less than 1% of the total arc length being measured, and the rest, like I said before, calculated with astronomical latitude. So again, for methods that are confirming the surface of Earth is curving, this one is also piss poor.
So, but proponents, you'll hear them say, like, all other projections besides the spherical globe one are, they'll be skewed, they'll be warped, they'll be off, right? It'll be, when you look at the legend, you'll start seeing how it falls apart and deviates from the globe, which is the only true one. And that would be because the whole entire coordinate system was sort of referencing us terrestrial sphere, like a celestial terrestrial sphere, like a two-sphere thing, right?
Yes, sir. So you got your your map projections are just projected geometry. So when they're looking at projective geometry, they're looking at projective coordinates versus geographic coordinates. Every map is projecting the same coordinate system, but their mistake is confusing that coordinate system is the Earth. It's not. It's the graticule. It's the gridded network of latitude, longitude, which, as we just went over, to prove that abstract coordinate system relates to the surface of Earth, you would need to use a geodetic datum, the ellipsoid model that we just went over. So maps by themselves certainly do not prove the shape of the Earth. Maps by themselves are just representing a spherical coordinate system. The actual argument isn't that the Earth is a sphere, that's why it works. It's that the coordinate system is spherical and that the orthographic globe projection is also a sphere. And that's why they have the match with the conformal and no distance and direction, because the base coordinate system is the thing that gets stretched and warped when you're trying to make projections. And if the base is the same as the projection, then the warping is minimal. So the big mistake that most globers make is they confuse the graticule with the Earth. And the graticule, again, is the gridded network of latitude, longitude, and the Earth is the surface of the Earth, right? So they would need to relate those with a geodetic datum.
But does it seem that as you move around this coordinate system, as people like from, I guess, actual travelers, that the same, what is it, 60 degrees, 69 degrees per 69 miles per degree, does that seem to hold true as you move, no matter where you move around, or does that maybe change based on the way the sky is actually, the way we see it, I guess?
I mean, that's a calculated metric. That's only ever calculated. It's never measured. And even in their model, it doesn't stay consistent by latitude. It changes as you move north and south, and it usually isn't consistent. It's really meant consistent north and south only. But when it's based on exactly the equatorial circumference of Earth. So we went to measure sun angles. We got an equatorial circumference of 24,901 miles. We divided that by 360. We get 69.87 statute miles per degree. That's what that's based on. Now, the thing about it is, on flat Earth, we have the same equatorial circumference. The sun does the same length of a circuit during the day. So an arc length along that circuit would be the same on either model. But, oh crap, what was the question? I just blacked out.
Yeah, I mean, pretty much answered it that even on their model, if it changes, it doesn't stay the same.
Right. 69 miles per degree. Yeah. So what we would need to do is to measure like 2 or 3 consecutive miles together and then have those see like, all right, did the sky actually precess 1 degree for 69 miles? Was it accurately measured? Because it's an assumption that actually we're finding with the celestial theodolite is entirely optics based. That gets a little complicated, but the apparent dip of the star that's 69 miles per degree is an apparent facet of your perspective. In actuality, the stars are actually up here, and you're only seeing them rise and set as they, precess. As they precess over you, they rise to the zenith, and then they set. But really, they're still going over here. So in reality, they could be in a plane. The true position seems to reference a specific consistent point that doesn't actually move at 69 miles per degree. That's optics based. But again, they got that measurement from looking at the sun angles and shadows and then using a known distance. The whole point of using an arc length to measure a circumference is silly. The Eratosthenes method says that he used, an angle of 7.2 degrees between Syene and Alexandria. And the other key component was that he knew it was 800 kilometers apart, or 500 stadia. So 800 kilometers is the known distance that you plug into 7.2 degrees over 360 times 800. And that's what gives you the circumference measurement, 24,901 miles. So the only way that has any physical meaning is that he plugged in 800 kilometers. So the only way it means anything is if you know a known arc length along this circle. If I know this is 800 meters, then I can calculate, obviously, the circumference of the circle. But you can't know something. You can't measure something by already knowing it. You can't measure the length of the circle by already knowing how long an arc length along it was. That doesn't tell you anything. Ratio of a circle, and that's my take on Eratosthenes.
So this is something I've said before. I just kind of imagine that if the sky, like if the stars were a plane, it would still sort of probably appear the same way to us. Right? Probably wouldn't even know.
Yeah, so in this wonderful model, right, if you turn around the stars and then you can have them form around the observer in an arc, or you can have them form as a plane, a completely level plane above the surface. And the way that the observer sees them in the model is entirely unchanged. So regardless of what shape the stars are in reality, whether they are in a plane or are in a dome / firmament, the way you observe them wouldn't change because of your limit of vision and the way you move around. You would always observe them in this hemisphere above you. That's what I think we concluded. So the whole point of the globe is they took this observation, and from inside this little guy here can't tell from looking at this hemisphere whether that's the top hemisphere of a globe or the hemisphere on the flat Earth of what you can see. The two things would be visually indistinguishable, right? You have no idea from within which model you were actually on. And that's the magic of the globe. And that's how they got everyone to know that when they don't see the sun, it's beneath their feet because Earth be globe.
I don't know what confuses me as far as like how they perceive their world. So as far as I'm just going off of perspective, right? So as far as the mathematical breakdown of our vision, how we see it, there's no exclusivity within it, right? So as far as to break it down, it can go with either model. You can spin it both ways. Just how they perceive the Earth. So as far as the sun going out in the distance and then going below the horizon, it just how far do you think? I'm not. It just I guess just thinking like a globe is just got me spinning. So I don't even know how to ask the question. So it's as far as how they perceive it based on how you can explain it. I guess it's just crazy to me. It's common sense based on perspective, in my opinion. Like things get angularly smaller, yes. It's just because you can't see no more doesn't mean it's over a curve. It's like why do they think it would curve right at the horizon? It's just crazy.
They're like, yeah, but the sun would never set if the Earth was flat because it's so bright and light travels forever. So obviously, I'd always be able to see the sun if the Earth was flat. That's such a fallacy. Like if you were in the desert and there was a car and it was at nighttime and it had headlights and there was no other lights and the car dropped you off and then drove off into the distance, you would see those lights get smaller, and then vanish. That doesn't mean that it went over like it didn't go over a curve. It became too small to see to make out and it took its light with it. Right. And that's what happens to the sun.
John used to come with some crazy strawman math, like vacuum math, no atmosphere, just disregard atmosphere, and talk about based on lumens, just how much further the sun would have to travel from an observer to have night, because we just can never have night. It would always be lit up. I was like, John, like, did you just leave out the atmosphere entirely? Well, yes.
Well, yeah.
Like,
So
why would
there's
we do that?
a
The conversation about Earth, where there's always an atmosphere.
there's a flat earth.ws meme, right, which shows like the Gleason's map and it's got a lumen meter, and then it shows again, it's the same argument that the sun, if the Earth was flat, I would never not see the sun because I know how light works and travels in infinite BBs that can bounce off anything and go forever and no matter what. It's like, okay. Listen, there's so much fault with that it's crazy. Obviously, flat earthers know that nighttime happens. So We understand that when the sun sets, it's too far away from you to see, and it simply took its light with it. Right? The daylight distribution over here is identical to the globe, actually. But we're looking at exactly the same thing, represented a little bit differently. It's the same data that's driving the model. It's the same representation of day and night. The lumens argument with the sun has crazy assumptions with it, right? Like through a vacuum, and then in that it would always be visible, and that you can see light forever, that there is no limit to human vision. Like you can see lights a thousand light years away as long as it's bright enough, right? That's their current philosophy, and that's retarded. That's retarded in like 7 different ways. You got contrast reduction, where at the horizon the colors would merge and become too bright for you to even distinguish anything from each other. The angular resolution limit of the human eye would have 2 things be indistinguishable based on angular resolution limit alone, well before they'd be, invisible via light. You have the inverse square law of light, which would drop off any visible source at a certain rate based on distance, proportionate to the square, that you would be invisible based on like 3 different factors. And that's just off the top. So assuming all that shit, they made that goofy meme that they try to, debunk flat Earth with. So power to them,
That's one of my favorite. Half impose what they believe to be true onto our model, completely ignore anything that we've,
Yep.
would argue, and then act like they, their conclusion is that they've completely destroyed our belief system with facts, logic, and science or whatever.
Yeah. That's
It's
like,
classic.
if the Earth was flat, the sun would be huge, you fucking idiot.
Dude,
It would take up the
it's
whole
like-
sky, dude.
It's like, well, dude, it would be huge for them too, unless they concede that they don't see like that vision isn't Euclidean, because the sun is 860,000 miles wide for them, but they see it as a half a degree in the sky.
Yep.
So if they see 1-to-1 forever in perpetuity, the sun should be the biggest thing in the sky. The whole sky should just be the sun.
Yep. I agree. Goofy.
Are any of you guys familiar with or able to like give your best steel man of that same, half a degree, like as it gets closer to the horizon, it pretty much ends up meaning that the sun has already set while you're still looking at. Like by the time the sun touches the horizon, it's pretty much already set, and it's just being lifted up half a degree on the horizon for what was that 2 minutes, for an extra 2 minutes, and vice versa. I don't know if anyone's familiar with that claim.
I don't even think that's exclusive to anything, right? That's like they're like, hey, on the globe, if the sun sets and then I get up on a tall building, I can watch it set again. Flat Earth destroyed. And it's like,
Oh, see, this one is that it's happening right before your eyes. That's the part that, like, I've been busting my head trying to even visualize what it is they could be
Talking about
doing.
refraction?
Yeah,
Like the
refraction.
refraction. Yeah.
So it's pretty much, John said this out loud, and I don't think he realized it. Like he probably never thought of it until he said it out loud at the time. That by the time the bottom, the very bottom part of the sun, like is touching the horizon like a tangent point, that's when it already set. That's the very moment that the top of it is kind of underneath the horizon as like a tangent touching, like fully set based on, half a degree and the speed, 15 degrees. Or what is it, hour?
well, have you guys seen this? Let me see. Can I change my stream? Yeah, here we go. Right, so sun sets on the surface, but our boy David Weiss. Oh, wait a second. Discord can't see my stream. Get rid of that.
Yeah, Dave's got some good ones.
Brave. There we go. Okay. Nope. Did it wrong. There we go. Right. So David Weiss has the sun fade out video, right, where it looks like, where'd it go? Okay, now we got it. Where it looks like it's fading out, but it's not, right? He raises the drone, I think it's 100 meters up, and he can still see the sun setting. So it from the surface, it's already set, and then he raises it up, and it's just fading out, and then it does one of these, right? Which is what it does all the time. This is the typical what the sun does. it just fades into atmospheric opacity and becomes indistinguishable. Didn't actually go below the horizon. It just kind of winks out. Like, and then the drone comes down. But yeah, so it fades out just like this most times. And in the right conditions, if you're at the right height, you can watch the sun not set, but just fade out, meaning it goes away until it's just not there. I think that's kind of the same argument.
Right, and then the intensity of light as well. So as far as like even when it's beyond the observer's horizon, regardless of elevation, you can still see the light in the sky. So that's an indicator to me that the light is local. Like it's taking this light with it, just like you said in the headlights on the ground. It's the same thing in the sky, it's just a brighter light.
Yep. Yep, that's my argument for that too. I like the sun fade outs. Wouldn't be possible on a globe. It's not unlike Stone's video on shadow sets, where we took an angular measurement of the length of the height of a shadow on a wall to say that the sun actually doesn't go below the horizon when it sets. And I think it was something like, I don't know, 73% of the sun was above the horizon at the time it set. So literally empirically proving a sunset like this when it's above the horizon and most of it is still visible, which would be geometrically impossible if sunset was caused by the rushing up of Earth curve, right?
I don't think there's a globe I've shown these videos to that didn't just like hand wave dismiss it as fake. Fake.
Right.
Well, the thing that gets me with the sunset now is because of all the self-theo talk, all the self-theo stuff. It's all about occultations or whatever. The stars are being occulted, and if the sun has set on the globe Earth, it's being occulted by the globe. So then, how the hell is it actually coming around the goddamn? It's actually physically blocked, so that they're just invoking magical refraction at that point. Something that, yeah.
And they're invoking it 1-to-1, which is what the Celthio has shown is impossible. It's definitely not 1-to-1. Like there is refraction, right? But the rate in which they invoke it to explain why we can still see it at a 15 degree per hour relationship is just what it mathematically needs to be to make it appear like it's not flat and it's a globe. Trust us. So like that's all it comes down to. There's a couple locations that I have to look into where we might be able to do some sun occlusions or emergences rather, that where we might be able to find out how much refraction they're adding versus how much there actually is. So
that would be big.
The sunset is just a big occultation. That's funny. I haven't thought about that.
Dude,
it's an Earth curve occultation.
That's what I Can Science Dad said to me when I first told him about the Celthio, because I was like, yo, I want to get you in on this, my dude. And he was like, well, hear me out. Right? The sun sets occluded by Earth ? I was like, no. That's what's I'm like, even if it was, that's what's in question. So we have to use the peak with different elevations to find out. And he was like, oh, okay, gotcha. But he did try that right off the rip. He was like, hear me out. Occluded by the Earth? Like, close.
Yeah, he was like, wait a second. Can I get out of this with flat Earth for can't sunset?
That's what he did. He literally tried it, bro. I mean, respect for trying, He gave it a shot.
Yo, but I still don't think anyone like knows exactly what I'm talking about. Maybe you've heard of it, but like because right on top of the horizon is about that half a degree. The claim is like you can watch the sun, like if you're watching the time lapse of its descent from the zenith all the way down, that it starts going into this little refractive band, I guess, the standard refraction, in a way that by the time you see it just touch the horizon, you're looking at an entirely refracted up sun that's entirely gone already.
Right.
That is absurd to just think of, like, how do you perceive, like, how did this just switch right in front of your eyes?
Have you seen Keyhole Sunset that it was doing with
the pinhole?
Well, the thing is that it's always apparent, right? But then as it gets closer to the horizon, the relationship in which it should be, maintaining its drop for the 15 degrees per hour as we rotate away from it, it lingers. So they're like, oh, what do we do? Oh, it's just refraction.
That fight,
Yeah,
yeah,
like
that's
it
what it
sounds
is.
good to hear it, but like when you start trying to visualize and think about how do you
Yeah,
even
so
explain what you're seeing?
yeah, so for them it would just be like the apparent object that we see that's normally moving at 15 degrees per hour is moving slower now because it's being lifted up more
Right.
because it's slower in the horizon, so there's more refraction.
Well, they do the same thing for the stars.
Yeah,
When so they call it the marine layer, right? Which is you don't see stars set right at the horizon. They stop like 5 degrees above the horizon because that's the highest atmospheric opacity, even at night. So you'll never see stars hit the horizon. They disappear into what they call the
Oh,
marine layer, right? That's the
what?
same thing.
No, I did not know
Yeah.
that. Are you kidding me?
Yep.
Oh,
Look it
dude.
up.
Dude, that's our oh my god. That's insane. That's so dude, we even
It
sleeping on
doesn't.
that? When did you
I didn't know what you guys were talking about. I was
when did
like,
you
wait, oh, you
find
mean this thing?
dude, that's a great art. That's our point. That's a great
Yeah,
argument.
I guess so. I guess yeah, that's even at night too. I was trying to apply it to the sun.
What would
No,
be the
that's
implications of
that
that?
that we have a natural limit of vision that's not due to the ball curve.
Okay, right.
Things disappear into the horizon, not over the horizon. Right. That's what that would prove
Oh,
because of the
okay, yeah, because they're
atmospheric
sitting
opacity.
above the horizon. Yeah, yeah, yeah. Interesting.
I like when you see the sun always set into that like inverted mirage of itself.
Yeah, that's extremely significant. What's the degrees on that? You said 5 degrees? That's a bit high.
I don't know. It is a lot. Hold on, let me look at
Yeah, that sounds a little large, my dude.
It's probably likely to be half a degree.
just
Because
what we're looking for.
as we watch the stars being occluded by really far distant peaks, the farthest we've ever captured was Greenhorn Mountain / North Peak, and that's just a little bit over half a degree. And by that time, they've faded out so much, you can't really make out the mountain that well. You can barely make out the stars except for the really bright ones. But that's right about half a degree, and that's where stellarium seems to wonk out and start giving us bad data.
Yep, and that's right where Jesse wants to take all of his observations and take all the conversations right to
Oh,
that half a degree.
that's what it, you use the globe matches down at the half.
Well, that's where it becomes gray enough to try and make a case for the globe. It doesn't even quite match, but it's indistinguishable, which is he's like, yes, I win, perfect. So, Teddy, this was a great prez for the Discord. You guys should hang out Discord more often. Visuals are fantastic.
Yeah, I got to get handy with it and learn how to use it. Will definitely be helpful.
Absolutely. Yeah, this was a great turnout.
Yeah, I actually have a question for one of y'all.
What's up?
Well, I'm trying to sell Theo out this bitch. So I'm in Virginia right now, right? So I was like, so we rented like an Airbnb, right? And it's like a huge farm. I don't know. They got like fucking. It's like close to like 700 acres of land they got over here, right? So I'm like, yo, like on my way over here, I'm like seeing a lot of mountain peaks and shit, and I'm like, damn, this might be a good spot, right? But unfortunately, when I got here, right, there's like mad trees like surrounding like the entire like fucking
Oh no.
yeah, like the entire area. But I'm leaving like Saturday, like I'm talking about in the AM, right? So tomorrow is my last day here. Unfortunately, today, well, maybe fortunately, today I see like a dip in the tree line, right? And I did purchase Peak Finder, and I was outside with Peak Finder, and I'm like, I see it giving me 3 peaks, and I already had looked in Google Maps. Like I checked the terrain version or whatever, and I see these like mountains that are out in that area. But then when I'm like outside in the yard, I'm looking at the alignment and it looks like it's blocked by trees. But now I went to the second floor of the house and there's a dip in the tree where I can actually see a mountain in the distance and it did align, and I think I got the name of that peak. So now I'm about to try to record to see if I could see a star getting occluded behind that peak, right? So now um I did have I did take a picture. It wasn't daytime, but I could do it tomorrow from exactly where I'm going to record, so that way we could overlay it, right? Um Now here's the question. If I happen to catch a star getting occluded, right? When I start the recording, like, am I supposed to like show the time, like, you know what I'm saying, like the time that I started recording, like with seconds and everything, and when I stop it?
If you know the frames at which you're recording, or if you could set it ahead of time to 1 frame a second, all you need to know is when you started the recording. So like if you can have it do the file name output as like a timestamp of when the file was created, and then just have your device sync to, GPS time, you'd be good to go.
I'm not sure, bro. I'm gonna record it from my iPhone, bro. So I mean, I can check to see like what is
Okay.
it
Yeah,
currently
if
recording at.
yeah, if it's yeah, there's probably a setting you can go to get it to one. But if it's your iPhone, we could figure out the frame rate, no problem, off of the model. So that's not that big of an issue. Just one is just convenient because it's just a 1-to-1 per second ratio. So that's just for ease of use. But um
Like
yeah,
would it be
yeah,
helpful
yeah,
like
yeah. You just need to know the time when you started the video, essentially.
yeah, because what I was thinking of doing, right? I already asked my daughter. I'm like, hey, do you have like a clock that like gives you seconds and everything? And she said, yeah, 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 I got one. So I was like, perfect. So when I start the recording, I'm gonna have her like kind of like in sync with me and show, you know what I'm saying, the time with the seconds, then I'll move it away or whatever. And then I could also, once I stop recording, record that time too. But that way we have a start time. You know what I'm saying?
Yeah. Yep.
Yeah, that's what I was just trying to figure out. How to get that start time in there. How important was it? Or do I just need the stop time? So
Start time. No, start time for sure. How to include
Also, make sure you take a
video.
recording of you taking the recording, or else they won't believe it's real.
yeah, I got it. For sure. I definitely will, bro. I got you.
On iPhone recordings.
Yeah, I got I think a 16 Pro Max, whatever it is. So what I don't remember
Oh,
is if
y-
I ever changed the
there,
settings like
there's an
to record. Yeah.
there's an app called Video Stamper or Timestamp Camera that you might be able to get on the App Store there. And if you record from within that app, you can have the settings to where it'll even put the timestamps on the video for you, so it'll timestamp it. But yeah, if you use that
What's it
to
called again?
it's called shoot, hold on, it's Video Stamper, and then there's another one that's called Timestamp Camera.
Are they free?
I have no idea.
Shit,
Mm,
video stamper?
yep.
Okay. I'll check it now. Thank you, bro.
Yeah.
Appreciate it.
Yep. But yeah, the most important part though is getting that start time synchronized for when the video started, because we can do the frame rate stuff later, and if we had to.
Yeah, I appreciate it. I'm telling my daughter right now to check so I don't forget the name of that.
Nice, yeah. And then there might be like other ones too. So like if you just in the app store just search for like video timestamp thing, and just see whichever one, because that's all you need.
So I'm looking that shit up right now.
By you mean her, right?
Yeah, I'm putting her to do it
Right,
while
right,
I'm
right,
on
right.
Discord.
Yeah, just so we're clear.
I would love to do selfie with my father. You're a good dad. That's pretty cool.
Hell yeah. Gotta teach him.
What's
That'd
up,
be so
everybody?
funny to have her Bring that to school.
Like, what did you do over summer break? I debunked the globe with my dad.
I
How'd you
showed the
do
surface of Earth wasn't
that?
curving through a null hypothesis observation with my father. What?
Definitely gonna tell her to use it as a nice science project.
Be so funny, dude. For her like fourth grade science thing, she's like, well, I independently on my own decided to use star occlusions to prove the shape of the Earth.
Dude, Ruhis made a video about it, right? But he gave up arguing any of the points, any of the true position, any of the stuff. He just argued that all distances are globe distances, and then that all observations are globe observations. And then he was pissed that we stole stellarium. He was like, and the audacity of them too. I guess you also stole stellarium to steal, and then they're gonna steal
Sure did.
stellarium, and then his next video is he's like, but that'll be the next time. So he's gonna make another video about how we stole stellarium next.
Nice,
So.
dude.
Totally do that thing with your kid. Make it the science project this year. Go in there and participate. Help her with the backboard. I mean, really, I did exactly the same thing with my first kid. We made actually, we both each made our own Bedini motor out of spinning CDs when she was in the 3rd grade. The science teacher comes by and looks at it, looks at me sitting next to it, smiling. She's there smiling. The fucking thing's doing 3,100 RPM on a 9-volt, and quiet as the bejesus, with a nice safety guard around it. And he looks at the backdrop, looks at me and says, "Did she make that?" I said, "Yeah, well, I wound her the coils, but she soldered everything up and mounted the bearings and yada yada." He's like, I think I might do this with my grade 7s next year." She was in the 3rd grade, bro. Like, seriously, think about it. Make it happen, man, because so few people actually do.
A quick question, if you guys could oblige.
Absolutely.
To my understanding, right, the Glover's response, or one of their rebuttals to the Stealthio, is that the terrestrial refraction makes it impossible to get the correct timing, right? But when you take terrestrial refraction into account, it goes the opposite of what the globe would need. Is that correct?
We don't calculate any refraction, and we have no problem predicting the timings.
Yeah, I understand that. But when they say, well, you can't take the right timing because you're not taking terrestrial refraction into account, and then when you guys even took that into account for their sake, it messed them up even more.
Oh, no, it didn't matter at all. It didn't help them in any way.
Yeah, and the Pikes Peak example, our 231 prediction is compared to 233. Their geometric prediction is 2 degrees 17 minutes. So that's very, very far away. If you apply terrestrial refraction, it's just 7/6R turns into 2.4 arc seconds per kilometer of lift. So then over 50.7 kilometers, that gives you like 2.1 additional arc minutes. So then that brings that 217 up to 219, but 219 is still much further from 233 than 231, right? So yeah, it doesn't help, but it does lift it back up a little bit more.
Okay. And they just completely disregarded that point.
Yep.
That answer?
Sure,
oh yeah, no,
sure
they don't
did.
hear that and they just say
Sure
it the
did.
next time.
So
Exactly.
so what the so cleverly, so Jesse, instead of disregarding that, he immediately realized like the issue and then started to try to use the true elevation to derive the distance and all that, because he's like, the refracted doesn't do that. You have to use the true position if we're doing an elevation. And it's like, yeah, no shit. But
That's the whole point, yeah.
but in doing that, he's not using the relative globe drop elevation of what his true elevation would be for an observer 50.7 kilometers away, because there would be 200 meters in drop. So you would subtract 11 arc minutes angularly from what it is in reality, and then that would give you what the globe predicts. And so he's trying to, like, on the back end be like, but no, I got to put that 200 meters back. I'm like, what? That's retarded. That's not even. That's
Yep.
You're creating an unfalsifiable thing that's not related to what already happened.
Except he doesn't say I have to put back that which I took away to make my judgment. He said Alan's doing triangles wrong. He doesn't agree with my. So he phrases it in the way that's like, no, you're doing it wrong. I should be able to both add in and subtract Earth drop at my own. Like if I want to make a prediction, sure, I take out the Earth drop. But if I want to measure stuff, I got to add it back in. Everyone knows that. Don't be silly. Like what?
Wait,
No.
so he is using the flat Earth angles initially and then adding back the globe drop after? Is that what he did? Because that's what I had a bet with John, I believe, on. I never really came back to resolve. I meant to speak to either. Because you
Yeah.
guys told me
So
he just lies about it. Yeah.
Yeah, so the tiny
Initially.
so the tiny angle that he started with to not use the flat Earth angle to start with ends up cooking him because he had to get the elevation and distances derived correctly. He has to use the actual values, which changes his just removes his initial prediction.
Right.
Yeah. It's unfortunate that he lies so aggressively about this thing so that people have a hard time grasping it, but that is indeed his goal.
We stole the globe. Hilarious.
Dude, Ruhiv said we stole 3 things. I forget the other thing. It was the celestial sphere model and then ended with Stellarium, but there was something in the middle that we also stole that he was mad about.
Stole Bislin's model?
Yeah, that was in there. But I still gotta steal his animation, dude. I love when he tries to make a debunk and he creates better visuals than I had. Like I'm totally stealing those visuals. Thanks, Ruhiv.
Nice.
That's gonna be in my GIF stash now, bro. It's gonna be in a video. It's gonna be backdrop. I'm gonna use that. Pretty full house.
Mm-hmm.
Wait, where'd all the Globers go? Did we not bring any Globers with you guys? Is everyone here flat besides coffee?
I'm pretty sure Coffee is a flat earther, bro. He just argues with us for fun.
I've been saying that for a while.
He's like the ultimate devil's advocate.
I was gonna say I'm a pretty staunch Glover. I've just been listening.
Oh, cool.
Nice.
Yeah, Josh is.
What's your favorite longitude if you're a Glober? All Globers have a favorite longi. What is it? What's yours?
Favorite longitude? That's a good question.
Is it though?
Let's see.
Hey, Jamal, you didn't introduce Josh in here, bro?
No, I got here late.
Yeah, I've been
hey.
incognito. Hey, you don't need to do all that.
So let's just say he's a professional glober, right? He's not an anti-flat earther, but by virtue of his occupation, he's a professional glober. All right, without him saying what he does, he's a professional glober.
Works at NASA.
No, it's fine. I have in the past, but no. Currently lead a team at Amazon, working on Project Kuiper, which is very similar to Starlink. So constellation of like 3,200 satellites to provide global internet. So I'm a senior manager there and lead a team of about 50.
Nice. I think you mean planar internet, though.
I mean, sure. Honestly, I was just listening. I would love to dive into at some point the coordinate transfer, because there's oh wow, it's the first time I've heard that.
Dude, your name's actually Josh. That's awesome. Okay.
Get fucked.
I'm sorry.
I like him.
No, I mean, I'm just listening. I would love if y'all could put the slide deck at some point in the main general chat of this Discord, just so I can peruse.
Absolutely. Can you put your Canva link in the? There you go. TY, sir.
Appreciate y'all. But yeah, as Linnell said, this is my job. I do a lot of science communication for the space industry and young professional mentorship. So taking lofty shit and trying to decompose it to be digestible is my whole thing. I'm not anti-flat earther, as I said, but I'm pretty staunch Glover.
We're in the
No,
same
we
line
can
of
tell that
business, it
you're.
sounds like.
No, we can tell you're not an anti-flat Earth douchebag because you're a normal person. So that's way cooler, way more interesting. You should meet our buddy Eric, who was a satellite engineer, and I think we all accept the coordinate system with which we're presented.
I think Mike used to be a satellite lad too.
That when he fight, yeah.
Interesting. No, interesting
Does,
presentation. I appreciate it.
hey, Josh, do you know that curvature of Earth and all the multiple motions like rotation, spinning, orbiting have never actually been proven?
I mean, yeah, you're riding in the car at that point. You feel acceleration, not velocity. If you're on a maglev train with zero friction, you don't know how fast you're going until you slow down or speed up.
You could use interferometry to measure that, though, to measure velocity.
No,
Here
because then
here
you get the
y'all were in
delta. If you
2004.
No, I understand that, but if you have interferometry and you have like the orthogonal laser set up, like um, mm, no, because then you would need relative velocities. I mean, I'd be happy to look at any papers you want me to read. Like I
Yes.
said,
Yeah, I'll send you some.
not here to
No, you're good.
like get all up and
No,
put
dude,
them up,
I would
get
much rather
fucked.
have like in-depth conversations with people who like understand the material or like are willing to like go over it than just like at like a media hand wave dismissal. So I'll send you the papers if you want to talk about them. Hit me up.
Yeah, dude, read
Sure.
some ether wind
Yeah, that's
papers,
fine.
talk about motion, interferometry. That'd be great. We love that.
There's a cool, if y'all want a paper to dig into, I put one in the general chat of this Discord a couple days ago. Professor
Oof.
at CU Boulder in like 2010, 2011, basically did like pixel mapping to some footage from Apollo 16 and 17.
Ballistic
Basically
motion of
like
dust
went,
particles. Wow.
yeah, yeah. And he like went frame by frame and backed out the parabolic motion and observed no air resistance. And using the relative speed of the wheel, was able to back out the expected around, like I think it's like 5% error, but right around the expected acceleration due to gravity that we thought, or that we state, is on the moon. Interesting stuff. It's one of my favorite papers when I'm you know looking at Apollo stuff, just because no air resistance, so they have to be in a vacuum chamber. Shit falls slower, so they have to be, if they're in a vacuum chamber, they're in a falling vacuum chamber, and then like thousands of dust particles. So trying to CGI that shit would fry a GPU today. And if we could do that, 60 years ago, why the fuck don't we have flying cars with teleporters now? So, it's interesting. One of my favorites, if you're interested.
There's definitely a graph about, let's see, the time at which it takes supposed dust particles to fall back down based on the equivalent ratio, but I don't know if that proves anything. I see your paper on the
If
moon
you go to
landing.
the references of the paper, they link
Yeah.
to supplemental materials if you want to download all of the Excel sheets as well as the overlays that they put on the images. So it's not just take their word for it. I've kicked the tires on it and actually spoken to the guy who published it. So um, definitely interesting. It's like I said, I really enjoy digging into this type of stuff, and that's one of my favorite, like, yeah, this shit's real type of deal.
Well, I see your paper. I raise you one footage of Apollo 17 using rainbow sparkles to power itself off the moon, courtesy of camera guy Ted, who get left behind forever or whatever.
I mean, I raise you image compression that records RGB values on subsequent frames. So anything with high motion is going to have chromatic aberration effects.
Oh.
They didn't actually. So you're saying that this dust diamond sparkles are aberration effects and not CGI
No, I'm
added
saying they're
afterwards?
white. I'm saying they're white sparkles that because of the high relative motion relative to the camera, they appear as rainbow because it's actually the RGB values being separated on each frame. To get full coverage, they had to get full color coverage through that small of a bandwidth channel. They literally like each frame took a separate color.
Wow, you were not kidding. You were a hardcore Glober, Josh.
Some of
Cheers,
the
bro.
best answers I've ever heard. Like, God bless. Hey, yo,
Bro,
how do we become
this is my
friends?
you just hit me up on LinkedIn.
There we go.
What the fuck?
Josh is the science communicator for his industry, man. He's one of the guys with the
Wait,
old
LinkedIn
school.
was real? You really? No one uses LinkedIn,
Yeah,
but
I'm not
all right,
fucking with you.
Okay, all right.
I got more followers than my VP on there, and I work at fucking Amazon.
I got a question
Josh,
about that. Oh, go
That's a
ahead.
red flag.
sorry, real quick. Josh, one
Go ahead.
thing that I didn't know that I learned is that there were hundreds of physicists slash astrophysicists whose work was censored and suppressed because they didn't go with the mainstream. Are you aware of that at all? Or?
I mean, it's one of the side effects of the peer review process. And it does lead to, fucking Galileo was ostracized by his community. Einstein was ostracized by his community. Like if you're going against the mainstream, it takes you, you know, it takes decades for somebody to like go like some grad student to go back look at your work and say maybe they're right and then do it again. So no, I agree. I agree that a side effect of the quote unquote open peer review process can lead to groupthink and folks that go against the grain being suppressed.
Yeah, but this isn't just, one or two isolated cases. These are scores, probably even in maybe the low hundreds or something, like a lot.
Yeah, like I said, if you have a primary source you'd like me to look at, I'm happy to. I'm happy to dive into it.
I was wondering, just since you're on a group that's creating satellites to be launched, what's the governmental audit process like? Or is that pretty intensive? Like, does everyone on the team get?
For unclassified work, which is like 95% of what the space industry is now, you only need a license like when you're going to operate, and that's just filing paperwork. The government doesn't come in and like look at your shit. If you're doing classified work, what you need what is called a FCL, facility compliance license, so that basically you need a government agency to come in and like check everything, and then you get what's called a secure. The fuck is the acronym? It's SCIF, CIF, sensitive compartmented information facility. So a SCIF is where classified conduct is conducted. And so that if you have a SCIF and you're doing classified work, you have like a government agency sponsor that comes in and like has to like make sure you're crossing your T's and dotting your I's. But that's only, like I said, that's like less than 5% of the work that's done in the industry. The vast majority is commercial.
You don't have like governmental guys coming to your house and shit?
To my house, like my house or the office?
Well, either or, I guess.
Me personally, yes. Like I hold a top secret clearance, and with 2 polygraph levels above DS. So
Okay, so
yeah,
so it is classified.
my handler's up my ass and around the corner sometimes. Like I need to ask permission to leave the country.
But they don't come to your house though, or do they?
They did during my initial investigation. Yeah,
Okay,
they came.
that's what I heard.
They
Yeah.
interviewed me. They interviewed my family, all of my immediate family, everybody I've
Yeah.
ever lived with for more than 90
That's
days,
crazy.
and like 5 or 6 of my friends that could serve as character witnesses.
But Josh, wouldn't you be compromised talking to us?
Yeah, I was gonna say.
Like,
What,
No, not
Chris, I
really.
found out
It's all it's all public information. I'm speaker trained at Amazon. Like that was a more intense process as far as like external communications. I'm not going to tell y'all classified shit. That's I walk the line.
Right.
Everything I'm talking about is unclassified. And
That's cool.
I'm not the fucking president. I can't have classified documents or have conversations outside of the appropriate environments without getting disappeared.
Yeah, I heard
But
that they like check your immediate family, and I thought that was pretty wild. But I mean, I get
oh,
yeah.
they got bank statements. They asked me about my kinks in the bedroom. Like, they asked me about, my history with mental health, what I talk about with my therapist. Yeah, they turn over almost every rock they can when you're
They
doing
ask
that
if you
type of
get your
work.
boosters.
What was that?
They ask you if you got your boosters.
No, I did that shit voluntarily.
Second red flag.
We don't need to discuss any medical procedures right now, though.
Yeah, I
But
was
we,
just
No,
but
no,
we
gonna.
it's
can
all good.
discuss kinks. That's crazy.
Well, I
Yeah,
mean,
no, they
Well,
do. They
definitely
do.
still
Because
screaming.
if if you were gay in time.
all right, lads and ladettes, thank you for tuning in to the Clubhouse Sesh, the premiere debut of the Discord Prezzies. Was awesome. Shout out to the awesome turnout. Shout out to everyone that came through. And let's see what we got coming up for the rest of the week on the schedule. Friday, we have community Twitter space. We'll join Twitter for a little bit and see what the lads and ladettes are up to. And Sunday will be Glowbusters, where I'll be going over the Jezzy Prezi for everyone. We'll recap latitude and longitude, how it can be independently derived from the Chinese method, and what the Jesuits proposed as the mutually exclusive, globe with the merger of the celestial and terrestrial spheres. So we'll get into all that on Sunday. It should be awesome. And then, of course, Monday will be Celestial Theodolite update number 16 or 17. I'll have to double check on that, but we'll be going over that. We'll be going over units of measurement because of distances. Apparently, apparently any distance is a globe distance. So we'll be going over that, the use of stellarium exactly. We even may touch on some latitude or some longitude derivations based on the Chinese methods, just to show the equivalence and how it's not mutually exclusive to use stellarium for this purpose. And then we will get into whatever else we get up to there on Monday. And then Tuesday, of course, will be Ether Roundtable number 98. And I think Shane's going to have something special planned for us. And if not, we will whip something up on the spot. All right. See you guys